this is the final part that we're going to look at our Boolean circuits with. And then we're going to move on to different number bases. And in this example, we're going to take a look at determining if two Boolean circuits are equivalent or not equivalent. And there's two actual ways to do this that are pretty simplistic. So first of all, you can compare the input-output tables. And then the second way to do it is just by a Boolean circuit or a Boolean expression. So circuit to the expression. So I'm going to show you both of these methods, at least for this first pair. So this is circuit 1. So I'm going to call this C sub 1. And I'm going to call this C sub 2 for our different circuits. And let's say we want a table for C1. All right, so that's going to be PQ. And we already know 1, 1, 0, 0, 1, 0, 1, 0. And then we have the output. And for circuit 2, we're going to have the exact same setup, but we don't know if it's the same yet. All right, so let's take a look, and we're going to pass all of the different ways that we can try to build the circuit through. Now, the good news is that as soon as you see a 1 for P, at least in the first circuit, it becomes a 0, which gives you a 0 for the output. So right away, those two outputs are 0. Right, we don't have to worry about those. However, we still have to worry about the 1s or the 0s for that. So anytime P is a 0, we get a 1. And the only time that this is going to work out to be able to give us a 1 here is when Q is a 0. Because if Q is a 1, that's going to produce a 0 there. That doesn't help us. All right, so this circuit was pretty easy to see that 0, 0 is the only one that we get a 1 out of. Right? Now for circuit 2, notice if we put anything with a 1 for P, we're going to get a 0 out of it. Right? So anytime P is 1, we get a 0. And the same could be said for Q. So anytime that Q is a 1, we're going to get an output of 0. So it looks like that the only time that this circuit is going to produce a 1 as the output is if both of the inputs are 0. Right? So this is a 0, and then this becomes a 1. All right, so what we can say is that since C1 and C2 have the same input-output tables, they are logically equivalent. Right? So that's one way to be able to do this. Of course, another way is just to construct the Boolean circuits. Right? So let me do that and show you how that could work out as well. Right? So delete all this stuff just so we have some room. Right? And I'll get rid of this while we're at it. No, probably won't get rid of it. I have to click on draw. That would be helpful. Just making a mess here. All right, so the input-output tables work nicely, but let's say for C1, we construct a Boolean statement. So that would be not P, not Q, and. All right, so we have the not P, not Q connected with an and. For circuit 2, that would be P or Q, and then with a not on the outside. And you might recall we could use De Morgan's law on circuit 2, and that would be not P and not Q. And so those are two indeed logically equivalent circuits because they have both the same Boolean statements. Okay, so we could say since C1, C2 simplify to the same Boolean statement, they are logically equivalent. All right, so that's nice. Unfortunately, if we try that method here, it might not work out to be a very nice result. Okay, so this might be an example where it might be more prudent for us to go through and just use the table. All right, and I don't really care which way you do it. In other words, you could use the circuit, the Boolean expression if you wanted to, or you could use the table. The table is a little bit more brute force, but in this case, building an expression for this might be pretty ridiculous to simplify. All right, so let's call these C1 and C2. And I'm going to start with C2 just because, well, it's easy. So we have P and Q, and then we have the output. We have 1, 1, 0, 0, and 1, 0, 1, 0. And as soon as we see that Q is a 0, then the output's 1. Right? So that's a 1, and that's a 1. And as soon as we see that P is a 1, then the output's going to be a 1 as well. So it looks like that 1, 1, 0, 1 is going to be the correct output. Right? And if I was to put 0, 1 through, then it looks like that this would be, so this 1 would become a 0, and then the output would be a 0. So it looks like that that is the correct output, just verifying. All right, now for this animal up here, we have our circuit 1 and P and Q and the output. So let's try 1, 1. Well, 1, 1 goes through here and gives us an output of 1. So that's good. Right? Nothing else will work because anytime you have a 0, like if this is 0 or this is 0 or this is 1, 0 or 0, 1, then all those outputs are going to be 0. All right, so now this next one here, it looks like the only way that this is going to give us a 1 is if we have a 1 here and a 0 here. So it looks like that the combination of 1, 0 will work nicely. All right, to produce a 1. And then right here, I think it's pretty obvious that if these are zeros, then that becomes a 1. And that's all of the different, I guess if we said that this one would work, if this was a 1, 0, so 1, 0 works, 0, 0 works, and 1, 1 works. Now, if we were to try the other 0, 1, well, we know 0, 1 doesn't work here. 0, 1 does not work here because of the 0 in this end. And then 0, 1 right here would produce a 0 here, and that wouldn't work. So it looks like that they are indeed logically equivalent, again, because the input-output tables are the same. So these circuits are logically equivalent by the input-output tables. All right, so we just have to justify why they're logically equivalent. All right. So the next section we're going to start taking a look at is a diversion from our circuits and our tables and our Boolean expressions. And we're going to start taking a look at number systems.